Okay, in chapter 8, we're getting into modeling. Not hand modeling, but modeling reality. And you can think of models like a globe. It's a model of the Earth. It's not the Earth itself. And the Earth isn't even a perfect sphere. So if the globe is a perfect sphere, it's not a completely accurate representation. So the first thing that I think you should know is, what is a model? It's something that represents reality. It's not reality itself. It approximates reality oftentimes. And a mathematical model is simply a model that has an equation tied along with it. Okay? Any questions on what a mathematical model is? In AP Stats, we will start with the simplest model possible, which is the linear model. Later on, you can discuss more complex models. George Box, a statistician, had this famous quote that's often used in statistics textbooks when they discuss things like this, and the quote is, "All models are wrong, but some are useful." And what I believe he meant by that is that all models are approximations. They're not reality themselves. But that doesn't mean we can't use them. There are many models out there that have small amounts of error and are thus useful for making predictions. Okay, any questions on number 2? It's important that you understand the difference between these 3 symbols. Y, naked Y, is the actual Y value that comes from the data. That's the observation. Anytime you put a horizontal line segment over a letter, it becomes the mean, in the statistics world at least. So that's the mean for Y. Anytime you put a caret symbol over a letter, that means that you are estimating that value. Okay? This is called Y bar. This is called Y hat. Any questions on that? Know what a residual is. All models have residuals tied with them because all models have error. That's what a residual is. It's the difference between reality and prediction. Know the order of subtraction. It's reality minus prediction. Actual Y value minus predicted Y value. That's the convention that we'll use. It's also helpful to know that it's the vertical distance between a point and the model. In our case here, a line. In this equation, they use E because of error. That's what a residual is, an error in prediction. Any questions on 4 or 5? Just some fun background information. The Netflix prize was a $1 million prize that went to the individual or group that could reduce the error in predicting movie or TV show ratings on Netflix. And more technically, it's the RMSE, which stands for root mean square error. It was about 0.95 stars, and they gave $1 million to whoever could reduce that by 10%. And it's not necessary to know this formula, but I'm just giving it to you. And I want you to compare it to standard deviation. It looks a lot like standard deviation. The differences is that it's not minus the mean. It's minus the prediction. And also, instead of n minus 1, it's n minus 2. If I have time later, I can explain why it's minus 2. But more importantly is that you understand what this means. And this will come up later. You'll see it comes up in computer output. So in my point of view, I would focus on interpreting this statistic. And this is just an average error. That's it. Okay. My main intent, though, for this activity was for you to see the line of best fit at work and to understand it better. The first thing I asked you to do was to graph these 3 points, 1, 1, 2, 4, and 6, 7. Those points are not collinear, and thus drawing a line of best fit is a bit of a challenge. But notice that your brain comes pretty close to what is considered the best fit line. So in pencil here is the first line that I drew to model that data. Remember, models are approximations of reality or simplifications of reality. The data is not collinear, It's approximately collinear, so I can use a line to model that. I wanted you to use your algebra skills to come up with the equation of the line that you drew. You need to have 2 points on the line. I chose 2, 3 and 7, 9, which is here. I found the slope. It was 6/5, and then I used that to find the y-intercept of 3/5. I put that together, and I got 6/5 x plus 3/5. Any questions on coming up with an equation of a line? I think it's important for you to know the graphical definition of a residual. It's a vertical distance between a point and the model. I indicated them on here. I wanted you to do so as well. So that's a residual, that's a residual, and that's a residual. Those are the errors. Please know how to calculate a residual. This will be required knowledge for you. It's pretty simple. Y minus y hat. Y comes from the data, so our first y value is 1. Y hat comes from the model. In order to get a value from the model, you have to plug in an x value. For the first point, your x value is 1. So all I did was plug 1 in for x, evaluated, and so my prediction here is 1.8, I believe, if my brain is working correctly. So the residual is negative 0.8. Keep the sign with the residual. If it's a negative residual, that means it's below the line, the point. It also means that you have overestimated because the model is predicting a value that's higher. Then do the same for the other points. Y minus y hat. The next y coordinate is 4. Y hat comes from plugging 2 into your equation, whatever your equation was. And the difference was positive 1 there. And then lastly, the last one. Often when you add residuals up, they sum to 0, and if we're trying to come up with a model that minimizes errors, and if the sum of those errors is often 0, it's not very helpful. We can't really distinguish models. So you have two options, or two main options, I would say. You can take the absolute value and sum those up, and there are some reasons for doing that, but for reasons that I'll plan on getting to, we don't take the absolute value, we square. That gets rid of the negatives. So that's the next step, squaring. So negative 0.8 times itself is 0.64. 1 squared is 1, and again, 0.64. Then to get a measure of overall error, even though it's squared, we can add those up. So the sum of the squared errors is 2.28. Any questions on 11, 12, or 13? Feel free to ask, because sometimes they don't think of everything, and it benefits others to hear those questions on the video. This line is the line of best fit. I understand that it might be difficult to draw a line that has a slope like 1.07. and a y-intercept of 0.79. So what I did was give you 2 points that are on that line. 3, 4, which by the way are the means. The means always fall on the line of best fit. So this is x bar and y bar. And then I also, when I plotted it, I noticed that it went through approximately 10, 11 and a half, or maybe it was exactly. I think it was exactly, actually. So I plotted those 2 points. I wanted you to do the same. So 3, 4 is there, and 10, 11 and a half is there. And then I use the straight edge to interpolate and extrapolate, I guess. So this is the best fitting line, the one in blue. This one has lower squared error overall than the one that I drew. But my expectation is that the best fitting line is close to the one that you drew just by eyeballing it, which is pretty amazing that the brain can do that. If you think that's an easy thing to do, try programming a computer or a robot to do that. you might find that it's quite difficult. Then, just like before, I found the residuals, same process, y minus y hat. I reiterate, know how to calculate residuals. Then, because these add up to 0, you can prove that to yourself. That's not very helpful. So I square them. It's just like with standard deviation. All the x minus x bars will add up to 0, and that's not useful if that happens every time for every data set. You can't use that as a measure of variability. So we square. And then add those squares up, so 1.93 squared units. That's a measure of your overall error. And notice that no matter what line you drew for number 8, you are not going to have a sum of squared errors that is smaller than 1.93. So this is considered the best fitting line. And the technical name for this line is the LSRL, or the least squares regression line. And this will be, in my use, synonymous with line of best fit. So when I say line of best fit, I am implying the least squares regression line. We'll talk later what regression means. But at this stage, I want you to know the least and the squares part, and also the line part. Okay? It's least because you are minimizing what? The squares. The squares of what? The residuals. So the LSRL is the line that makes the sum of the squared residuals the smallest it possibly can be for any set of data. And back in like the mid-19th century, we did not know this, and people were working with data quite a bit. So now you have the advantage of your calculator being able to find the slope and the y-intercept of the least squares regression line instantaneously, which I'm sure people back then would have liked to have had. Again, any questions at all on that activity? So hopefully you have a better understanding now of the least squares regression line and how it works. All right.